In this lesson, we're going to take a look at some techniques in one of the most essential abilities throughout the development of an effect or a scene, which is population, and also deal directly with some vector manipulation to really start to control our rotations and how our effect evolves throughout the different angles. Here, what we have is we have a collection of broken shells that you might find on a beach. And it has a few characteristics that would mimic reality. For instance, there aren't a whole lot of shells where the slope is very high. And that just makes sense because they'd either fall down or they'd stay up higher here. They're also more or less facing in the direction of the flow of the current of the water. See, they're facing as they would flow. They're not facing sideways because the current would have kind of pushed them along their path of least resistance. So let's set up a scene like this. We're also going to get into a bit more advanced copying techniques because we don't want to make a gazillion copies. We actually want to make a more unique copy of different fractured parts of our shell. Okay, so here's the setup for reference. And let's start with a few basic pieces already made. So I'm starting with a shell. There's my shell. And I've performed a fracture on that. And we're not going to go into the fracture right now. There is another class in the fundamental series that addresses fracturing. Okay, so here is a nicely fractured shell, and we really want to take these shapes and use them for all that they can be used for. Okay, and now we've got a nice little slope that has some variation in it. Okay, so the first thing I want to do is I want to figure out where these shells should go and what direction they should be facing. So I'm going to start off by dropping down a VOP, which is our vector powerhouse. And let's try to figure out where the most and least likely areas, where the population areas are going to be throughout this. So what we can do for that is we're going to get the dot product. Okay, so the dot product is synonymous with the angle. And let's just set a direction for what up would be. So actually, we can just make a constant for that. So this is going to be our world up vector. There we go. And then we want the normal, and to get that, we have to use the facet to compute the normal of the terrain. So this would be, as we post-compute normals, this is going to set the normal to the polygon normal. So now we have a direction facing outwards from the surface, and let's compare that with the dot product. Okay, so in comes our normal, in comes our up, and then when we put that into the color, we're not going to see much yet because there aren't a lot of differences, but let's remap that. So the dot product, it'll be -1 if it's opposite, it'll be +1 if it's completely the same vector, and if it's a right angle, it'll be 0. So here, let's start by fitting the result of this dot product from its current range, is just -1, 1, to the range of a ramp, which is 0 to 1. And now I'm going to start by remapping that with a curve. Okay, and notice I'm previewing this in the color, just to make it easier. Okay, so let's see how this plays out. All right, so as we really take down this tolerance, we see we're pulling values away from the most different, or the most similar angles, actually the most different angles from up. Okay, so if up's this way, then this white area is going to be very similar. This dark area is going to be very different. Okay. There we go. Okay, so let's kind of put a little bit into there. It's okay to have a little bit of shells in there, just not a whole lot. And I'm just going to make that transition a bit smoother with a B-spline interpolation. There we go. and we'll have most of the focus here. All right. Cool. So that's where our shells are mostly going to be populated. So following that up, let's make this an attribute to get this information in something other than the color. Color is great for previews, but it's not a very good way to actually do useful things. So I'm going to put a parameter down. We'll call it pop for population. Export when input is connected, and we'll export that. We can leave it plugged into the color for a preview, but the color is not necessary anymore. Okay, so as we scatter, notice that it's completely even distribution right now. There's an equal number of points in the dark versus the light. I'm going to take off the relaxation because this is a non-organic life form. They're not going to repel each other per se. And let's put the density up a little ways. Okay, so that's a lot of shells. And now I'm going to enable this density attribute to pop. And what you'll notice now is that it's only populating scatters where it's a high value of our pop attribute. And that's what we want. Okay, now let's get them to flow in the right direction. So we already have the surface normal, and that's great for our up vector. It's great for the tilt axis. We're going to have the shell being aligned. Its up direction is going to be locked onto this terrain like this, but we need the flow direction, the direction that it would be facing down its z-axis, where the water and the current would be making it flow in this way. How do we get that? Well, that's the cross product. So we want to say, okay, based on the flow of this direction away from the surface, I want the vectors to kind of be flowing in that way too. So I'm going to start off just by making a single point, and this is what I'm going to use to control that direction. Okay, so here's our point. It's just existing one point. Let's use a point wrangle. And I'm just going to set the normal. Vector at normal equals brackets close expression and 0, 0, 1. Okay, so we've just got a plain old normal facing down the z-axis. And now, because it's a vector attribute, I'm going to use the transform to rotate it around. So it's already in the right spot, but we'll be able to demonstrate by doing this to change our flow direction. Okay, so in another VOP, we could use a VOP here or down here. I'm going to do it up here just so we can see the flow a little better. I'm going to get, we already have access to the train normals. I'm going to get attribute to get data from the second input. Okay, so second input goes into file. We want to gather the normal attribute, 0.0, and that's it. Now we have access to the normal from the second input. All right, and what we want to do is we want to compare this, and we want to have a perpendicular vector. So for that, we're going to use the cross product. Okay, so the first cross product is going to be the only vector that is crossed between these vectors and our input vector. Okay, so it's going to be somewhere pointed out to the side there. There we go. Okay, now it's kind of adhering to the terrain already. Notice it's kind of flowing in this direction. And that's cool if that's what we wanted, but we want it to actually flow in the original direction, just, you know, aligned with the terrain. So we want the direction of our normal aligned with the terrain. So we're going to take this and cross that with the upwards normal. So we're going to take this result, cross that with the upwards normal, and then we should get a flowing direction. There we go. So now these vectors are nicely flowing in the right direction that we want them facing. And just to demonstrate how that works with our direction here, we can see we can easily adjust how the flow would work. We can adjust this if we had a fluid sim. We could actually get the directions from the velocities off of fluid sim. Okay, and our points will inherit that normal. And lastly, let's just put the up. So I'm going to normalize this. And let's put the up using the previous normal, because this will be our tilt axis, is outwards from the polygon surface. Okay, so up, vector, invisible, when input is connected. There we go. And now we should have a really nice set of axes. Okay. So we have that. And now let's just do a random scale. So a great way to see the scale in the viewport is by enabling disks under geometry display. And now we can see, once we add a particle system anyway, we should be able to see the actual P scale. Okay, so let's do a random scale. All right, so random number generator. In comes the point number. We're going to fit the random to our desired minimum and maximum. And export that as a p-scale. We already have a proper size variation curve because we're using a fractured object, which will naturally have more small pieces than big pieces. And now we can see our display changes. Actually, we don't need that particle system in this current scene. Okay, and that's a really fast and easy way to preview our size variation in the scene. So I'm going to start by getting the lowest conceivable value, which would be maybe tiny little shell there, something like that. And then I'm going to dial that up for the high value, maybe something like that, large shell. Now we have all the information we need to make a great copy of one shell, but this fracture has lots of shells present in it. So each one of these would be a little shell bit. Okay, so how do we navigate that? Well, each one of these shells has a name attribute present from the fracture. So if we look at the name attribute, we have fragment 5, fragment 9. Okay, so one way to contend with that is I want to set all of these to the origin. How do we set them all to the origin and align them? We're dealing with kind of the same situation which you just did, but in reverse. Okay, so how do we like reverse align these things? That's going to be a technique that'll really help you out and navigate through more complex setups. So let's for each loop through each named primitive. And what this is going to do is it's going to go through and gather each piece by piece and do whatever operation is in between these two things. So I'm going to say single pass, and I'm going to try to find a larger shell to test on. And there's a great looking thing. For me, it's a single pass of 4. Okay. Here we go. Okay, so the first thing I want to do is I want to figure out what the longest direction is here. I can kind of see from the viewport, but how do we procedurally figure that out? So for that, we can use a box. And by default, the box, as you saw there, is not very informative. We don't really know which side is biggest. But if we do an oriented bounding box, then it's very clear to see that the smallest side is in this direction, and the largest side is what the direction of up would be, which is that direction. So now it becomes very easy to get those vectors. Okay, so I'm going to measure these sides. We can use the measure SOP. Okay, and let's measure the area, and we can see that this is the small one, and the red one is the large one. Okay, and now, because we don't know which polygons those are, we're going to sort by that attribute, primitive sort, by attribute area. And now it's guaranteed that the smallest polygon will be polygon 0. Okay. And faceting that, post compute normals like we just did, and unique points because otherwise the directions are averaging. Unique points, there we are. Now we'll easily be able to get the direction of the smallest polygon. So polygon 0 and non-selected. There we have it. So there's the direction of the smallest polygon. And to finish that up, I'm going to just take point 0 with another blast, and now we'll change this to points non-selected 0. So now we have a nice little vector. We were successfully able to compute the direction of this shell. Now we want the upwards direction, the tilt, and that's going to be this way. Okay, so that would be the largest polygon, the direction of the largest polygon. Okay, so that would be this guy. It's already polygon 0, but we need to procedurally figure that out. So now after this sort, this is sorted by area. So we're going to do reverse sort. Primitive sort, okay, actually just reverse primitive sort. And now if we blast 0, we're left with the largest polygon. And we have a nice little direction vector here as well. Okay, so let's change this. Let's rename that. Actually, we don't need to do anything with it. We just need to somehow align this piece to have this as its up direction and this as its normal direction. So I'm going to start off just by putting this piece in the middle. And we can use the transform stop for that. Okay, and here I'm going to go to translate. We want to do a negative center of x. And that will subtract wherever the center was off the origin back in the other direction, and follow negative center of y, negative center of z. Okay, and what that's done is it's placed our piece in the middle. If we wanted to, we could base our rotational calculation off of that instead. Okay, we're still going to get the same vectors because it hasn't actually rotated. Okay, and now all we have to do is rotate it opposite of what these are. So we can use an inverse rotation for that. So our normal, our direction is going into the second input. Our upwards direction is going into the third input. Okay, so we need to make a rotational matrix out of these two vectors. How do we do that? So get attribute, we need to get the normal off the second and third input. 0.0, and that's done. Okay, so vector, second input, point attribute, normal, 0.0. Call this direction. I'm going to call this one tilt. All right, now how do we make a rotation matrix out of this? So for that, I'm going to use a really handy VOP, a lookat VOP, and this is exactly what the copy SOP does. How to calculate its rotations once you feed it a normal and an up. One caveat is to make sure that you say from is the origin 0, 0, 0, and then it's going to be looking in this direction using this as its tilt. And now we have a rotation matrix. And to reverse that matrix, we'll just do an invert. There's our inverted matrix, and now we would apply this as a parent, like in rigging, and our positions of each point will be the children. So we would multiply our positions, make them children of the rotation. There we go. So now you can see that its longest direction is the positive z-axis, and its upwards direction is the largest polygon on the flat surface. Okay, and doing that to all of the pieces, here it's just single pass of 4, but if we did this to all the pieces, then we have this very nice collection of pieces ready to be copied. All right, and because we want to have this as an area optimized copy, I'm going to assemble this. And what this is going to do is it's going to pack, you probably have heard that term, packed primitives. So it's going to be kind of compacting each polygon, each set of polygons, each name into these primitives. So I'm going to do create pack geometry. Do not create the name attribute. We already have the name attribute on there. And we want the pivot location at the origin because we've already determined what the origin is going to be. And now if you look at it, it goes from 36,000 points, it's gone to 800 points. Yeah, each one of these points is like a little object. So it's a way of kind of working procedurally with similar to object level data. Okay, so these are ready to be copied. So here's the next issue. I don't want to copy 800 points on each of these 10,000 points. I actually want the same number of these as these. How do we do that? Well, we can just use the copy sub for that. We'll do a copy and transform or duplicate. Okay, and total number, you see, as we increase this, it's just going to make more and more of these points. Okay, so we need to know exactly how many to make. So we're going to get the number of points from this. I'll just set down a little placeholder here. This will be num, so 10,000. Okay, so we want the number of points in our input. We want this guy divided by this guy. Okay, so point or n points, number of points in dot dot slash for a path num. Okay, and you might want to go to manual mode before you hit enter. So I'm going to hit escape here. Go to manual mode because I don't want tons of copies. Okay, so n points num. Okay, and now that made 10,000 copies. We do not want 10,000 copies of 800 points. So instead, we're going to divide that by the number of points in the input. So number of points op input path of myself and the 0th index. And that has gathered 12 copies. And that's no problem. So we've got 10,152 and 10,403. So just so we're always over and never under, I'm going to add 1 to that. Okay, so now we've got almost 11,000 to 10,000, and if we have more fractures or more points, then that'll procedurally adjust. Okay, now we want the exact number. So now we just delete the overage. So with a blast, we're just going to remove the ones that are greater than that number. So let's say we want to keep from 0.0 to point backticks for evaluate whatever we put in here as an expression first and then turn it into a string. Okay, number of points in, once again, num. So we want only these points, non-selected points. Okay, so now we have 10,404. Here we have 10,403. Okay, so number of points minus 1. 403, 403. All right, so you have the exact same number of points here and the exact same number of points here. So the only thing left to do is to put these objects, these packed fragments, onto these. And once again, we can't use a copy for that because it's going to make 10,000 points onto 10,000 points. We don't want that. We just want one thing to go into the location of this thing. So let's do that using our raw vector math. Okay, so we just want to put this guy and make it go into here. I'm going to go in that location. All right, so just want to move it around essentially. So with packed fragments, you can use the transform intrinsic. So the transform is keeping track of the rotation of that object. So the easy one is the position. That's not in the transform. So here, let's just set the position to the position of the second point. So I'm going to get the position off the second input. Get attribute P, current point number, because they both share the point numbers, and we go there. Okay, so already we're off to a good start. We're at the correct position. Oh, and if it seems too ordered, then we can always sort our copies randomly. Point sort random. Okay, so now we have a completely random assortment of combinations here. Okay, so there's that. Now we want to rotate, and that's a little harder, but that's no problem because we can use the same technique we just did. We can use the look at. We're going to get the normal and the up vector, just like the copy SOP would, off the second input's points as well. Once again, set it from the origin 0, 0, 0 to the direction we want to look at, using this as the stabilization axis. And now I just want to export this as the transform. Okay, so for that, we're going to use a set attribute. We want to set a primitive intrinsic. So it's going to be a matrix 3 primitive intrinsic set transform current primitive number, and we want to do that here. And now we've rotated that into our right rotations. So you see how it's nicely facing down on the slope, and it's got its largest axis pointed up in the air. Okay, and now let's just apply the p-scale. So that we can also do the matrix. Okay, so here we're going to do a scale. Okay, so we just want to scale that by the p-scale. So I'm going to get another attribute, p-scale. This is going to be a float, and I'm going to turn the float into a vector. There we go, and apply that. All right, and now we're taking the size of the shell and scaling that. So here we really just want to adjust our numbers a little bit here. Let's do that to get our smallest piece, and that to get our biggest piece. The reason these copies are so efficient, even though we have millions and millions of polygons, is because it's using a packed geometry. So it's actually an instance in the scene. We don't want to unpack that because then we get thousands, but this will render and copy very efficiently. And now we've learned a little bit of our way around raw vectors, and that'll really help anyone's progression into more advanced effects work.